Okay, for section 1.3, we're going to look at the strength of an acid base or an acid and a base. What do we mean by strong versus weak? Then we're going to look at pH, and we're going to look at the pH of strong acid and the pH of strong bases, which are sufficiently concentrated. Again, remember this slide that I told you that eventually that's all you're going to need for this acid-base chapter, not for the full course, but for the acid-base chapter. So at this part, we're going to discuss this end. Okay, we're going to look at strong acids, strong bases, where the concentration is greater than 3.2 times 10 to the minus 7. We call this a sufficiently concentrated solution. Well, it's actually not very concentrated, but it's sufficiently concentrated. Okay. To begin with, I'd like to define what a strong acid is and to differentiate between strong and weak. Strong acids are those acids which dissociate completely to H3O plus and the conjugate base in solution. And honestly, for me, I really want you to know who these acids are. Okay, there are only 6, so we may as well memorize who the strong acids are. Everything that is not strong is considered weak. Okay, so what are these strong acids? Well, first of all, we look at the halogen end. It's the HCl, HBr, HI. Notice HF does not belong to this category. Okay, so it's HCl, HBr, HI, followed by H2SO4, which is also considered diprotic. However, it's only the first deprotonation of the sulfuric acid that's considered strong, and we will get back to that later on. Nitric acid and perchloric acid. Okay. These are the 6 strong acids. And believe it or not, there aren't much more than those. Okay. The strong bases also dissociate completely to give OH minus in solution. And I really do here mean dissociate, okay? Because the only strong bases in aqueous medium, I'm talking, are the group 1A and group 2A hydroxides. And better list than this is the one before. But anytime you look at the first row in the periodic table, sodium, lithium, potassium, rubidium, all of these are hydroxides, are considered strong. And the second row, also most of them are considered strong. So we also have calcium, strontium, barium hydroxide, which is group 2A metals. The earth, so the alkali and the alkali earth hydroxides. Guys, whatever is not strong is considered weak. Okay? So weak acids and bases, they dissociate partially. They don't have complete dissociation or complete reaction with water when they're reacting. And usually whatever dissociates is normally less than 10%. And some important just examples of these, some weak acids. HF is considered a weak acid. Acetic acid is a weak acid, that's its structure. It's this H that's gonna get deprotonated, not these ones. Cyanic acid, HCN, okay, and this is formic acid, and it's this H that dissociates. In organic chemistry, you're going to look more at the acids and what makes an acid stronger or less weak. Remember resonance. You also have and so on and so forth. You will take that in organic chemistry. For us in general chemistry, all you have to concentrate on, if I have a strong acid, At the beginning, for example, HCl is a strong acid. This is initial, before ionization. At equilibrium, or when the reaction is complete, guess what? All of my HCl has split up. If you look at the solution, there's no more HCl anymore. Everything, single molecule, has been transformed to either H plus or Cl minus, okay? So there's no more, and again, you don't see any H plus, you see H3O plus here. That's your H plus, okay? Weak. For example, HF is a weak acid. At the end, so this is before, at the end, at equilibrium, and here it's an equilibrium because it doesn't completely dissociate, we have some, and most of the HF has not dissociated. Only a small amount has been formed of the H plus and the F minus. And that's actually what distinguishes the fact that at equilibrium, at the end of the reaction, I will have absolutely nothing left over of the initial acid, while in a weak acid, most of that initial acid has remained in solution. And so if you look at the solution, we have all the HF, and only a very small amount has dissociated into the F minus and into the H3O plus. And so repeat before ionization, after at equilibrium. If you see that you have none of the HA left, that means this is considered a strong acid. If most of the HA is left, that is a weak acid. And the more there is left over HA and only small amount of dissociated ions, that means this is a weaker acid than this one would be. We're going to discuss weak acids in our following up recording. Percent ionization is always 100%. And if I look at the initial concentration of acid, you know, it doesn't change, and there's no effect on percent ionization if I change the initial concentration of acid. So if I have higher concentration or a lower concentration, my percent ionization is absolutely the same for strong acids. And for weak acids, we're going to look at this. How does the initial concentration decrease the percent ionization as I increase my initial concentration? Don't worry about this graph. We will see it a little bit later on. So here's just sort of cutoff. We have some strong acids and we have some weak acids. And the reason I put this for you is I really want you to read who are these acids, because you have to get a feel for, you know, what acids are out there. So we have nitrous acid. Notice nitrous acid is not strong, it's weak. Yet nitric acid is strong, okay? And these are the conjugate base of the acid. Remember, that's when I remove the H and you get the anion left over if it's neutral. Okay, now all of these strong acids, they give us, when they remove their proton, get ionized, we get these conjugate bases. I just want you to get a rule for this. These conjugate bases, they're called conjugate base just because, you know, that's by definition. But are they really bases? They're not, okay? In solution, because again, there's no back reaction whatsoever. So these guys do not end up re-reacting to form the starting acid, okay? None of these. So all of these are considered spectator ions. They do not react to go back. So Cl minus will not react again to reform HCl. We will discuss H2SO4 later. So all of these, the conjugate bases of the acids, are considered spectator ions and non-reactive ions in solution. Okay, a little bit of a different concept at the moment, but to gear up for the next part, I do have to discuss this now. The pH. How do we measure pH? We measure pH using a pH meter. And pH stands for potential hydrogen or hydrogen potential, okay? And actually, it's a voltmeter, which measures the potential difference between two different electrodes. So we put two different electrodes. Here's one of the electrodes called a glass electrode, and we put another reference electrode. And then we put a solution of some unknown solution, whatever it is. And overall, okay, this whole setup is going to form a galvanic cell. And we're going to discuss galvanic cells when we get to redox reactions. And I'm sure you've already seen that in lower levels of chemistry courses. You're going to get a potential difference, okay, and between these two electrodes, and that pretty much measures our pH, okay? And it indicates the pH variation. Well, not worrying about, you know, the mechanism of how pH meter works, it just does, okay? So if I take a Pepsi Cola and put a pH meter of whatever shape or form it looks, we get the pH of Pepsi, okay? And here it is, it's 3.12. The pH scale for these pH meters is from 0 to 14. Now, if you measure and you get a pH that's negative, it means that you have a problem with your electrode. So watch out for that. We're not going to discuss anyways. pH is outside this variation from 0 to 14. Here's just some examples of gastric juice, lemon juice, the different pHs. Look at milk, it's almost neutral. Well, if we get pure water, it would be 7. I highly doubt we're drinking pure water. Household ammonia, which you see a lot in detergents and cleaning agents, are very, very basic, and it's 11.5. Okay, our pure blood is 7.4 and whatnot, okay? Okay, so pH. P of any x, P of x is the minus log of that x. So pH POH is minus log of OH minus. Okay? Now, why do I need to say this? Is because I don't have a meter that measures basicity. Okay? I only have a pH meter, but it's from this pH meter that I can get an indication of how much basic my solution is. I'll give you an example. You already know that autoionization of water that gives me H plus times OH minus is KW. I take the minus log of both of these sides, minus log of H plus, and remember the multiplication of a log, you do the addition of those two logs. So minus log of OH minus, or plus the minus log of OH minus, equals minus the log of KW. Minus log of 10 to the minus 14 is 14. And we have this wonderful equation, which tells me pH plus POH is equal to 14. So anytime I measure a pH, I can get the POH. It's simply 14 minus pH. As well, if I have the pH, I can go backwards, guys. Like it's like a minus log. If I antilog or get this value of H, it's the antilog. So the H will be 10 to the minus pH. This is mathematics, which most of you know. And if from the POH, if I want the OH minus concentration, it's 10 to the minus POH. Okay? So that's from this antilog of this equation. And make sure that you know how to get, how to use your calculator, how to do, the antilog and things like this. So make sure that you know how to do these calculations. Different calculators do it differently. That's just what I just said now. And so how can a pH meter, which ranges from 0 to 14, measure basicity? And you already know that we have a cutoff scale, pH equals 7. And pH equals 7 is our neutral. When we say something's neutral, it's pH equals 7. Anything below 7, we say it's acidic. Anything above 7, we say it's basic. Okay. Now, for us, anything close to 7, it's actually really the concentration of H and H3O plus and OH minus. They vary, but they're not too much off. So here we have a pH scale plus or minus 1. You know, this is where the concentrations doesn't really vary. If my medium has a lot more H plus than OH minus, actually, we call this a major amount of H plus, then it's below 6. And if my OH is the major species and its concentration is much higher than H3O plus, and actually more than 1/10 of H3O plus, then 10 times the amount of H3O plus at least, then it's 8 and above. Okay? But we don't actually set that up. All we say is neutral, pH 7, that's when these two guys are almost the same concentration. Of course, this is only in pure water. And if the pH is less than 7, we say that the H3O plus is greater than 10 to the minus 7. And it's considered basic as long as the pH is greater than 7. And that means that the H3O plus is less than 10 to the minus 7. Okay. Look at a little bit of an application of this pH and variance like that. So the pH of rainwater collected in a certain region in Lebanon on a particular day was 4.82. So they actually collected rainwater and they took the pH and it came out to be 4.82. What's the H plus concentration? So I have the pH, I want the H. So you put that in. This is a number I have. I want this. Okay, so I could use this equation. H plus is simply 10 to the minus pH, and put that number in. Please make sure you know how to do this in a calculator. That's the only reason I put this question, that I want you to start using your calculators. If you were in class with me, I would have gotten you all right now to open up your calculators and start doing these calculations, because you have to be very fast at them. Next question. The OH ion concentration of blood sample is this amount. Okay, so now I have the OH. What is the pH of this blood? So now I have OH, I want the pH. Well, we know there's a relationship between acidity and basicity with the fact that pH plus POH is 14. So since I have OH, I could easily get POH minus log of OH is the POH. That's that. So that's my number, my concentration, minus log. Again, use your calculator. You get POH is 6.6. Substitute back in here, and voila, you are done. You do this in another way. And remember, we could use KW from the OH minus, get the H plus concentration, which is plus would be KW divided by the OH minus, so divided by this number, and then get the pH once you have the H plus concentration. This is going to be a little bit of a long recording, but all the information comes in together in one shot, so I have to talk about it. So remember, we talked about strong acids being completely dissociated. And if you remember from our introduction, we said when we have 99% dissociation, or alpha is 0.99 or alpha is 0.999, that's complete. Called this quantitative, we call that complete. That we consider these reactions to be 100% or one-way reactions. Okay? And acids pretty much go like this, one-way arrow, complete dissociation of whatever I have at the beginning. And that this Cl minus, okay, this conjugate base, we no longer consider it a conjugate base. We say it's a conjugate base, but we call him a spectator ion because he's not really a base, he's not gonna go back. There's no back reaction, even though he's reacting with H plus, come on. This should really want to go back here, minus and a plus charge. It really should want to go back, but it doesn't. Okay, which tells you that this CL is really, really a spectator. He's just looking around. Even if he has H plus, he doesn't react with him. All right. Now, pH, remember, is minus log of H plus. Now, if this is a one-way reaction, that means whatever my initial concentration here will be my final concentration of the, and I don't really care about Cl, so my final concentration of plus, or H plus, is simply my initial concentration of HA. So pH is simply minus log the concentration of the acid, whatever it is. So if my concentration of acid, what's the pH of an acid? That is 0.00836 molar. Well, I just use this equation. Of course, this has limitations, okay? And we're going to talk about these limitations later on. But for now, do believe in me and say that I could use this equation as long as my system or my concentration of acid is greater than 3.2 times 10 to the minus 7. And this is called sufficient concentrated solution. So that's my cutoff. As long as this concentration of acid, strong acid, is greater than 3.2 times 10 to the minus 7, I could simply say pH is minus log the concentration of that acid initially. And this is only for strong acids, okay? Everything I'm going to talk about here is either strong acid or a strong base. I'm going to go a little bit of a detail here, So, what is the pH of a 2.2 times 10 to the minus 3 molar nitric acid? So first thing you have to say, what is this acid? You have memorized already the 6 strong. So this is a strong acid, okay? Now, most of the time they will tell you it's a strong acid, but you know, I want to make sure that you do know them, okay? So this is a strong acid. The idea of strong acid means not that it has a high pH, but that it 100% undergoes ionization completely. So one-way arrow. Again, there's no such thing as 100%, but one-way arrow. And we're going to start, I'm going to put an ICE here table, initial and end. And remember, there's no need for a change here. Initial concentration. Let me go one step at a time. Initially, I only have the nitric acid and 0 of the ions. Okay? So we have 0 ions in solution. At the end, I will have 0 concentration of the nitric acid. That means that my X amount of reacted is 0.02. So here plus X, this will be 0.02 and 0.02. Remember, with one-way arrows, I only need initial and, you know, infinity, if you will, or T final at the end. pH is minus log of H3O plus, which is minus log of the initial concentration of the acid, which is also minus log of this H plus, which is minus log of 0.002. And here's my pH. It's acidic. It is greater than 7. And so, yes, I have an acidic solution. Of course, you don't ever need to put this chart, guys. I just showed it to you now. But you never, ever have to use it. All you need to do is pH equals minus log the initial concentration of the acid. Okay, so use that equation directly. Of course, this is with the limitation that the initial concentration is greater than this number, 3.2 times 10 to the minus 7. So we're going to look now at base, okay? Strong base. NaOH is a strong base. And if its concentration is 0.001, what is the pH? Okay. So again, strong base, 100% dissociation or ionization or whatever you want to call it. And again, this reacts with water. Once it's in aqueous form, it can dissociate into Na plus and OH minus. And so I have a certain amount of OH in solution. And because this is one way, whatever initial concentration of NaOH, it's going to be the final concentration of OH minus. It's also a 1-to-1. Just to point out, with acid base, it's always a 1-to-1. Okay, with acid base, always a 1-to-1, at least with what we're doing. We're going to look at that even with diprotics, and you're going to see that. Okay, so here's my OH minus concentration. What can I do? Get the POH minus log of the OH, and POH is 3, and then I can get pH. pH is 14 minus the POH. Of course, you could use this equation, which is pH equals 14 plus log of the base. Why? Because minus POH is minus log of the base concentration. So this becomes a minus, so it's a plus. So you can use this equation right away. If you're asked for the pH of a base, simply say it's 14 plus log of the concentration of that base, whatever it is. And you can take a look at this using another way. I'm not going to get into it. Okay. Again, this is under the concentration where it's greater than 3.2 times 10 to the minus 7. I will repeat this number so you can memorize it. What's the pH of this base? Okay, barium hydroxide, and they're giving you the concentration. Again, barium hydroxide is also a strong base. It's a group 2A hydroxide. But now we have 2 OHs. Okay? So when this dissociates and you get a balanced equation, you end up getting 2 molecules of OH. If I have initially 0.018 molar, at the end, we get 0 of the initial base. Solid, but it becomes in the aqueous once it's in water, and then it gets dissociated. Regardless, this is a 1-to-1, so this is also going to be 0.018, but this is going to be plus 2x. Multiply this concentration by 2. And here we have concentrations chart all the way. At some point, we may have to use some other form of a chart, but when we get there, we get there. And here now, POH is still minus log the concentration of OH. But here the concentration of OH is 2 times the concentration of the base, okay? And then you get the pH 14 minus POH. So sometimes, yeah, you have to watch out for the bases that give you 2 molecules of OH. So when we say concentration of base here, okay, we really mean the concentration of this OH minus, all right, in solution, not the concentration of this initial OH, especially if it's not a 1-to-1. So you just have to watch out for this trick. And again, these concentrations have to be greater than 3.2 times 10 to the minus 7. And this is a part, section page 221 in your textbook. It's called the leveling effect of water. Okay, the case of a strong acid, strong base. That in the case of a strong acid, strong base, okay, in water, the acid gives the H3O plus, okay, and you always have the strength of the strong acid in water is leveled to that of the H3O plus and water couple. Okay, so everything in the H3O plus form is equal to the strength of that acid, okay, or whatever the concentration is, it will all be converted to the H3O plus. Same thing with the base. Whatever we get leveling off of the strength of the strong base in water. So the strong base, everything that comes from the strong base, the OH minus, will be leveled off to that of the couple water OH. So this couple will have a concentration equal to that of the OH. Now, don't worry much about this, just know how to do the calculation and you will be fine. Just as a final note, please do not confuse strong and weak with acidity and basicity. Remember, strong acid is one that dissociates completely, and a weak acid is one that does not dissociate completely. So the word strong is by its nature. Okay? It's the nature of the acid. It's either strong or it's weak. It has nothing to do with its concentration. I mean, I could have HCl concentration 10 to the minus 6, 10 to the minus 9, but it's still a strong acid, okay? Regardless of its concentration. It will still dissociate completely in water. However, the word acidity is a measure of the H plus concentration. So we could have a strong acid that has a low acidity. Okay, it can have a pH of, say, 6. Okay, it can have a low acidity. And this acidity varies with concentration. Okay? And so do watch out and don't confuse the two. At the end, we're going to have to go back to this each and every time I finalize something. So we discussed strong acids. And we said that a strong acid, the pH is minus the log, the concentration of that acid, okay? As long as the concentration of this acid is greater than 3.2 times 10 to the minus 7. We also discussed strong bases, and we said that the base pH of a base, strong base, is 14 plus the log of the concentration of the base. Remember, the concentration of the OH minus in the solution coming from that base. Okay? And that's in the case of strong bases. That's also in the case where these concentrations are greater than 3.2 times 10 to the minus 7. So we're done with this end of this table. Voila.